Okay, so today we're beginning our discussion of experiment 23A. We're only doing part A of experiment 23, and this concerns the amide synthesis of acetanilide. So this reaction is run between aniline and acetic anhydride. Acetic anhydride is an activated acylation reagent, an acylating reagent. And the mechanism for this reaction is a textbook carbonyl substitution. So your amine attacks the ketone carbon. We generate the following tetrahedral intermediate. That tetrahedral intermediate then collapses and we lose acetate as our leaving group. And then for our final step, acetate pulls off a proton and we generate our neutral acetanilide and acetic acid. So if you run the reaction in person, you can actually get a sense of whether or not the reaction is occurring efficiently based on the smell of acetic acid, which gives a faint hint of vinegar. We use an excess of acetic anhydride in this reaction. So for your limiting reactant calculations and for your theoretical yield calculations, you'll have to use the amount of aniline. Another thing I'd like you to add is that aniline has to typically be purified before use. This is a common characteristic of amines in that they can oxidize readily during storage. So as such, we take our quote unquote crude aniline solution and we purify it over activated charcoal before transferring our aniline solution into our reaction vessel. Activated charcoal is great for removing metal impurities and other colored impurities, and it's a common cleanup step used during filtration and treatment of your product. If you want to get a nice off-white yellow solid, typically rinsing or passing the solution over activated charcoal usually helps to remove many of these very polar colored impurities. Does everyone understand what's going on so far for this reaction? So we have a mechanism, so you should include this mechanism. And I'm discussing sort of how we treat our reagents in order for our reaction to run efficiently. I'd like you to note that this treatment step results in a small amount of loss of material, but not enough for it to have a significant impact on the yield. Okay, so in terms of practically how this reaction is going to proceed, we're going to mix our solution of aniline and acetic anhydride. The acetic anhydride is used in excess. One, because acetic anhydride is readily reactive with water. And the second reason for this is your acetic anhydride, if it's added in excess, if any side reactions use up the acetic anhydride, we still have more than enough equivalents of our acylating reagent to complete the reaction. So at the end of this process, our only byproduct is acetic acid. So we are going to observe in our reaction vessel, our solid product will slowly begin to precipitate out of solution, and we can isolate our product via filtration and rinsing with water. There are other rinses that you can do if you're concerned about removing impurities, but the lab procedure just calls for rinsing with water. I would like you to note that although the lab manual mentions recrystallization, we did not need to do a recrystallization to collect reasonable spectroscopic data. Also, if you tried to recrystallize the scaled up version using the glassware that we have in the laboratory, you'd overload your Craig tube. So recrystallization is not necessary for this to get a reasonably pure sample. This is a very robust reaction, and it's wonderful in that the impurities readily evaporate upon drying. So we're going to record the mass of purified acetanilide. Just as a side note, have we seen this compound before? Have we seen this compound in any previous experiments? This is a compound that we studied all the way back in the physical properties laboratory in Chem 112. It's a nice, robust compound. It's pretty easy to measure physical properties for. The reason why I'm bringing this up is you probably have a table with the data for acetanilide in one of your old reports. So you may want to copy and paste that data into your new report for your physical properties table only. Okay, so once we have our solid, we'll measure the melting point. You'll calculate the percent air. That gives us a sense of the product identity, and the melting point range, which gives us a sense of the product purity. We're going to take the IR spectra in NuJoule. One thing I'd like you to note before you start assigning sp3CH peaks, NuJoule is a hydrocarbon. It has sp3CH bonds, and as such, you'd see this giant peak. That's the NuJoule. Don't worry about it. In terms of this structure, you'd still be able to see some of these sp3 peaks as well. You'd also be able to see the aromatic sp2 peaks. So there are plenty of very diagnostic peaks in the IR spectra. We'll also take a proton and a carbon NMR. I provided this on a higher resolution instrument, 400 megahertz. So that way you can actually assign multiplets, doublets, triplets, etc. So notice we're also taking a carbon NMR in this case. So you're going to want to have the spectral data for your reactant and product. So you need the IR, proton, and carbon NMR for your reactant and product. Just your reactant and product. You don't have to worry about the solvents or byproducts. Just focus on the principal, reactant, and product. So aniline and the acetanilide. Now, in addition to spectroscopic data and melting point, this is the first example where we apply solubility tests. This is found in chapter 9 of your book. You'll see a characteristic flow chart in chapter 9. You're going to need to read the entirety of chapter 9 to be familiar with the chemical tests utilized and to be familiar with this solubility flow chart. We'll talk through each of the chemical tests and solubility tests and talk about the goals of these solubility tests. So fundamentally, solubility tests are useful for assigning the chemical identity of different compounds. Water solubility is a key differentiating factor, and we find that amides are water soluble while amines are not. So we can differentiate between our reactant and product based on the water solubility. Further, an interesting quirk of amides is that they're litmus neutral. So when you test the pH of the solution, you will see a roughly pH 7 solution by testing with litmus paper. Does everyone get that first distinction, the first thing to look at from the solubility test? Now, 5% sodium hydroxide, you'd expect your amide to not be particularly soluble in that solution. The 5% hydrochloric acid test is very important to discuss because the amines are soluble because you generate the ammonium salt, while the amides are insoluble. Does everyone understand how the 5% hydrochloric acid solubility test allows us to infer whether we have an amine or amide? Perfect. So let's keep going. So for concentrated sulfuric acid and concentrated phosphoric acid, these will give a positive test for solubility for our amide. And these serve as additional verification that we have an amide. The final solubility test is in ether, where amides are ether soluble. So it's important that you record the results for these solubility tests And by interpreting your observations from these solubility tests, you can conclude whether you have an amide or an amine. For our further chemical tests that we'll be performing for this lab, we're doing the hydroxamate test. And the hydroxamate test serves as a critical test for an amide or ester. So in this test, we are reacting our amide with hydroxylamine at elevated temperatures. This results in a carbonyl substitution reaction where we replace our leaving group aniline with this hydroxylamine. This generates a hydroxamate, and this hydroxamate has a very unique property in that it can readily coordinate iron. So your iron 3 chloride is a yellow solution. However, when it coordinates a ligand, specifically when it coordinates a hydroxamate ligand, you end up observing a characteristic color change and you see a red-violet color. So appearance of this red-violet color upon mixing your iron 3 chloride and your generated hydroxamate is a positive result. Does that make sense to everyone? Perfect. So the other test we're doing is the soda-lime test. And the soda-lime test, not to be confused with the sodium fusion test, is a specific test to detect the presence of nitrogen in your compound. In the soda-lime test, you mix soda lime, manganese dioxide, and your product. This is an exhaustive oxidation reaction that frees up nitrogen in your compound in the form of ammonia gas. So by heating this mixture, you will slowly generate ammonia if nitrogen is present in your product. And that ammonia, considering ammonia is basic, will result in a color change using either brilliant yellow or litmus red paper. You'll see a characteristic color change as the ammonia interacts with your litmus paper. And that color change tells us that ammonia was generated, and as such, the product contains nitrogen. Does everyone understand the purpose of the soda-lime test? It allows us to confirm the presence of nitrogen. So by combining the observations from each of these tests, we can conclude whether or not we prepared acetanilide or whether we have aniline still remaining. Finally, we're going to be dealing with the ignition test, which confirms the presence of an aromatic ring. We've seen this time and time again. Burning a compound containing an aromatic ring generates a dark and sooty flame. So that's an overview of today's lab. Pretty straightforward reaction, all things considered. The main bulk of this lab is dedicated to analyzing the spectra and the chemical test results. So, any questions on this lab? I provided a recording that showcases a large-scale prep and recrystallization, just so you can get a sense of how these reactions are run on a slightly larger scale. Any other questions on this laboratory? Okay, so we'll be archiving this recording. One moment.